Very good, thank you. Okay, so full disclosure, I'm not an astronomer by training, so I'm an interloper, but I'm learning as I go, and for sure, a lot of the techniques that are developed in different areas, including those in high energy physics that Ashley was pointing out, can be applied more generally. Okay, so I'm first going to present a few ways of I like to think about characterizing anomalies. There's many different axes, and these axes can be useful in identifying what are the different kinds of assumptions that are going into the models and how we might design tools to look for them. So one set of axes are the latency axis and the supervision axis. So latency axis here is how much time do I have to make a decision, basically. We've been talking a lot about transients, and transients can be fast, they can be slow, and what fast and slow mean is how long it takes to do follow-up, how long it takes to do an analysis, and there's also a stark division between things you can have to do online, that is, like say, in real time, and things that can be done offline, even if they're still need to be done quickly. So I'm going to be basically focusing entirely on offline, more or less here, and there's a whole suite of challenges that arise online that I'm happy to follow up at the end if there are questions. A lot of the methods that have been developed, especially those that are density-based, don't work online because of the YOLO nature. If you only get a look once, you can't do things like estimate densities, and that's an interesting challenge for these kind of tools. The other axis is the supervision axis, so that is I'll give a couple different ways of thinking about this in the next slides, but how much information I'm going to assume about the structure of the problem. And so unsupervised, I don't assume too much at all. I don't give any label information for the learning. And if you have supervised is the total extreme, and then somewhere in the middle there's noisy or partial label information that I can provide, and that is another interesting spectrum. Okay, another way of thinking about this problem is on these two different planes, which is how much model dependence am I going to put into the development of a tool. So there's two questions you need to ask every time you have an anomaly. The first one is like, is it weird? Okay, and how do I figure out if something is weird? And the other question you have to ask, which is often forgotten, is how weird is it? And so the first question, is it weird? When you think about how to find something that's weird, you first have to figure out, you will rely somewhat on what you think the normal stuff looks like, the background, and also what kind of things you're looking for, the signal. So classical searches for new things often will have, say, like a simulation or a stand-in for the background and the signal. You can train a model, classical or whatever, machine learning based, to distinguish them, and that's your kind of a normal approach. So it lives down in this bottom corner. But you could imagine other strategies where live in these other parts of the plane where you try to assume as little as possible about, say, what the anomalies look like or about what the background looks like. But then once you have an anomaly, you have to figure out how weird is it, especially because we're often looking for statistical anomalies. No individual example is anomalous, and so I need to be able to figure out how anomalous it is by looking at the context. And the context can also depend on what the model of the signal is and what the model of the background is. So for the signal, maybe you have to know something about like how often it happens, and that will help determine how you would figure out how anomalous it is. Okay, my third picture here, which is Ashley touched on a little bit, is different kinds of anomaly, or point anomalies versus group anomalies. I'm going to put all of the non-point anomalies into group anomalies, but more or less, the point anomaly, as you see a single example, you show it to an expert, it's an anomaly, Nobel Prize. Okay, that's like kind of how it works, and we almost always are never in that case. Sometimes we get lucky, like when the positron was discovered 100 years ago, that's more or less how it happened. There was a charged particle going through a plate and it was bending the wrong way, and okay, boom, Nobel Prize. But that usually doesn't happen. Usually it's a group anomaly where there might be, say, like in this picture here, instead of a flying pig, there's a few more pigs than usual at the barn, and I have to know the distribution of pigs to know it is weird, okay? And that's a much harder problem, but that's why it's an interesting problem. Okay. So now let me drill down a little bit, thinking about some more, dissecting this a little bit. So on the supervision axis, there are many different strategies, and the strategies are often connected to what you're assuming about the new stuff will look like. So these are the unsupervised, weakly supervised, semi-supervised, supervised. This is all about labels. So what information I'm going to teach the model as it tries to look for some new structure in our data. The weakly supervised, semi-supervised, I would say is not, whether it's noisy, partial labels, somewhere in between, there's a whole spectrum of tools, and not everyone agrees on the nomenclature. Okay, so unsupervised, really here I have no labels, and typically the goal of methods developed to do unsupervised anomaly detection are looking for events or objects that have a low likelihood. So underneath the null hypothesis, the background only hypothesis, you have some density and they have a low probability of being like the background. And there are a number of different strategies for doing this. I think Ashley mentioned in her last talk that someone used an autoencoder. So autoencoders are of this class. And an autoencoder, for example, like the one shown here, is you try to automatically compress and uncompress the data. So imagine you have image-like data. You can learn to compress and uncompress at the same time. And when you take some new data set, some new point you haven't seen before, you compress and uncompress it. If it's not uncompressed very well, so the original and the compressed, uncompressed look very similar, then likely it has a low density. That's because your compression algorithm should be spending most of its its bandwidth on things that are common. That's how compression algorithms work. And so things that are rare, it should not do a very good job at those. So that's sort of an indirect way of probing the density, but you can also probe the density directly by training, say, normalizing flow, which is an algorithm that tries to model the actual probability density of the data, and you can use a normalizing flow, for example, to also find anomalies. Okay, that's unsupervised. There's a whole class of algorithms that I'm just going to call them weakly supervised, where you have noisy labels. And here, one set of these kind of tools are cases where, say, you have two sets of events or objects. And one of them might be signal enriched, one of them might be signal depleted. I mean, we're never in this situation where you have lots of signal, right? It's an anomaly, so like they're both almost all noise, and then a little bit of signal maybe. But having these two samples to play off each other, you can think of them as having noisy labels in the sense that the signal enriched is like noisy label signal, and the background is like noisy label background, and you can play them off each other to find something new. Okay. So that's just two examples, and I want to focus on these two because it's interesting to see the trade-offs between the two approaches. So for, first of all, there's the anomaly assumption. So for the unsupervised methods, we're assuming that the anomaly, if it exists, is rare. And for these weakly supervised methods, for example, let's say you want to train a classifier to distinguish these two data sets, you're assuming that you have two data sets for which the signal, if it exists, is more prevalent in one than the other. So it's overdense. And there are many different assumptions that go into these different tools, but from a statistical point of view, the main drawback from my perspective of unsupervised methods is that it depends on, rare is not universal. So if I change my coordinates, rare can change. So that's a key challenge. I mean, forget about even picking the features. If you just have the same feature set and just rotate it, you get different rare. Well, rotating won't work, it's linear transformation. But nonlinear transformation, you'll get a different set of anomalies. And for weakly supervised, you need the two samples. So it's not always possible to construct a reference either from data or from simulations. Okay. So just super quick a note about coordinates, because unsupervised anomaly detection, like with autoencoders, are extremely popular. So I just wanted to, I think it's not always appreciated, this is a feature of them. So this is like a super trivial example. Let's say you have two Gaussians. If I apply linear transformation to the Gaussians, like on the top left, say like my x are my Gaussians, and I apply 2x plus 5. Okay, so I just moved them around. That doesn't do anything. What's anomalous is still anomalous. Because it's a linear transformation. But if I say do e to the minus x, so it's a nonlinear transformation, I swap where things are, and the tail that was on the right is now kind of in the core of the distribution for the yellow guy. And so even if you could get the exact density, which autoencoders do not do, and there's all sorts of questions about autoencoders versus variational autoencoders and whether it's learning the density or not. In this case, you have to be careful about how you pick your coordinates. Okay, and I just have, this is one slide just to compare, let's say, unsupervised versus weakly supervised. So say you have the left picture here, say it's Gaussians, right? So I have two Gaussians, and there are three different colors, and the different colors correspond to different transformations of the Gaussians. So there's the solid lines, the three colors are different methods, the different kinds of lines are different transformations. So the solid lines are Gaussians, then the dashed lines, I apply the inverse CDF of a Gaussian, so it makes a Gaussian look like uniform distribution. And then the dot dash is I apply a tan H, so it's another nonlinear transformation. And then there's the red is a normalizing flow, the green is an autoencoder, vanilla autoencoder, and the purple is weakly supervised, and where I happen to have a reference. Okay, and so the purple lines, they all look exactly the same because likelihood ratios are invariant under coordinate transformations. So that's a benefit of doing likelihood ratios. It doesn't depend on the coordinates. They're exactly the same. And for the other ones, you can see that, first of all, their performance is less, because for unsupervised learning, I'm not telling it anything. So if it's good at finding something, it's just basically by luck. And they vary depending on the coordinates. So that's an interesting challenge that unsupervised methods face, is that there isn't like a limit in which they're optimal. and they suffer from this choice of coordinates. On the other hand, the right picture here is another example of this anomaly detection, where in this case it's from a collider physics example where we're comparing as a function of the strength of the anomaly. So how many anomalous examples there are. And the thing about unsupervised learning is it doesn't actually care, because you're not asking how much signal is in this data set, you're asking what looks like not the background, basically. And so it doesn't care how much signal you have in your data set. Its performance is independent of how much signal you have. So that's a benefit if the signal is very rare. Whereas some of these other methods that use the presence of the signal to find the signal, they do very bad when there isn't that much signal, and they do very good when there's a lot of signal. And so that's why you see this kind of crossover point between unsupervised and weakly supervised. Okay, and this is AUC, and it's not the full story. You could ask the question, does that orange value, asymptote of the orange value, is it a useful amount of power or not? And it depends on the context. Okay. Okay, so now what I'm going to do is show a worked example from astrophysics using stellar streams. So this is going to be in the context of a resonant anomaly. So resonant anomalies are kind of a subclass of, it's a group anomaly, it's a subclass of these weakly supervised methods can be deployed to them, where you have some dimension. Here I have m. You can tell I'm a collider physicist because the m is the invariant mass. But here it could be time, it could be many other things. And so whatever, if the anomaly exists, it's localized somewhere, and then the background of it is just featureless. Okay, and then the idea is I need to generate noisy labels. So I could create a region near where the anomaly is, and then a region away from where the anomaly might be. That will give me my noisy labels, and then from there I can use other features, whatever other features are available, say spectra or positions in the sky or whatever else, to try to find the weird stuff. And in the context of stellar streams, here's some pictures of some stellar streams. It might be, so because all the streams are basically the remnants of protogalaxies, because all the stars in the stream came from the same protogalaxy, they're moving with roughly the same proper motion. So proper motion is like a resonant feature. So in that sense, I'm looking for an overdensity in proper motion of stars that kind of look similar otherwise. And so the other dimensions that I can use would be like the location in the sky, metallicity, all those kind of things. And so this is like the example I'm going to give. All right. And so this mu here is the proper motion. The background stars on the left in one particular patch of the sky it's featureless. It's kind of smooth, and you can imagine constructing a signal region and a sideband region away from there. And the stream stars in this particular case for this simulated stream, they're localized. And so just using this one dimension alone, you could try to find something that's overdense. But you can also use the presence of other features. In this case, this is from the Gaia data set, so there's many dimensions. And you can use those to try to tease out additional events. Okay, so for example, if you look at GD1 is a particularly nice bright stream in the sky. And these kind of machine learning methods, they work. They can automatically identify the presence of the stream and the stream stars. I didn't tell it anything. All I told it was look in this particular patch. And this is sort of complementary to all the existing methods for finding streams, which rely a lot on astrophysics, which is great because we know a lot about astrophysics. But if you want to look for things that go beyond the assumptions that are built on the astrophysics, then these kind of tools can augment those strategies. So here, this is just highlighting that basically the machine learning method finds all the same physical features that the classical method finds, so these like gaps and spurs and other properties of the stream. But you can also imagine going beyond that. So you can see that the stream found by machine learning is not as regular looking. That's because it doesn't just draw a big box in some high-dimensional space. And that might be useful for understanding structure that goes beyond the assumptions that were in the classical method. And some of my friends, I wasn't part of this paper, but basically took this and scaled it up to the full sky. And have found a number of interesting stream candidates. These are some pictures of stream candidates that merit follow-up to see if they're really streams or not, using this automated method, methods like this to look for overdensities in this high-dimensional space. Okay. So yeah, the left picture is a location in the sky, and the right picture is this, in the proper motion. In addition to finding the streams, we can also use these tools to identify new properties of the streams themselves. So, for example, we found in GD1 a number of stars that look like they're consistent with the stream, but they're not labeled by the classical catalogs of GD1. And so that merits further follow-up, and maybe that will allow us to learn more about the structure of these streams going forward. All right, the last slide of content is, this is now some ongoing work to think about how we might try to integrate more model dependence. So everything I've said so far basically ignored everything about astrophysics except for knowing that they're localized in proper motion. So now if you had a bunch of simulated streams, for example, how would you incorporate that into the learning task? So in this particular case, we have like 100 mock streams, and we could train, say, a supervised model. Like the simplest thing to do is to train a supervised model on all the streams, just all at once. In this case, it's a big graph neural network on all the points inside all the stars inside the stream. And that's the red line here, has some performance on some holdout set of streams. And the blue line here is if you do this weakly supervised method, so I don't know anything about astrophysics. All I have to say is localized somewhere. And the x-axis is how much of the stars I randomly throw away. Because I want to say, as I mentioned for these weakly supervised methods, if you throw away stars, it does worse. If you have all the stars, it does better. And there's like an interesting crossover point. And that actually depends on which streams you're looking at, and there's kind of a trade-off between the kinds of modality. Like if the streams you're looking for look more like the ones you trained on, obviously they'll be better at finding them. And so there's an interesting trade-off between imposing more information or not in building these tools. Okay. I've only scratched the surface of what's possible, and it's really exciting to see science start coming from these tools to automatically find new structure. We definitely need new R&D in addition to adapting tools for astrophysics and also thinking about, I'm really excited about time domain astronomy. I've so far focused not on time domain, but time is an interesting dimension for making things resonant. So a lot of these tools basically should just apply. And I think it's also exciting to think about developing data sets that can be used for benchmarking and testing these kind of tools. As a small plug, we actually have a NeurIPS challenge, a cosmology challenge this year for which anomaly detection will be an interesting component, and happy to say more about that later. I think that's it. Thanks.
So you mentioned that when there were these stars that one stream finding method identified as part of the streams and another one didn't, that they would be interesting targets for follow-up. And I was wondering if you could say a little bit more about what sort of follow-up would resolve that discrepancy.
Yeah, so we, in this, let me see if I can go back to that. Yeah, here, for example. Yeah, so we published just like a list of whatever the neural networks that are the most anomalous, are the most likely to belong to the stream. And this, from the Gaia data set, for example, they have limited spectral information. So you could try to get a spectrum. And I'm not an astronomer, but I'm told that will help distinguish if they belong to a stream or not. And maybe someone who knows more can tell me if that's true.
I just wonder if you could say more about where you think the most exciting methodological development is in this space and in what role new time domain data might play in that.
Definitely. I mean, for sure, a lot of the development in industry has been on point anomalies, because for a lot of industrial processes and other things, that's what you care about. And we almost never care about that case. But a lot of anomaly detection has been applying those tools to these problems. So like autoencoders and other tools, which are very powerful, but there's a whole, their power is limited, basically, for the reasons I've tried to stress in this presentation. So I think, especially for time domain astronomy, where you have this context from the stuff, it's transient. That's exactly the opportunity to develop new methods or adapt methods that can use this reference information from the sideband in order to do better anomaly detection. And so I think that's going to be quite exciting.
Okay, let's thank Ben again.